Only one guy is online.
Sir.
Yeah, Murli, right?
Yes, sir.
Okay. Any others are joining or not? Shri Kritik, any idea others are joining or not? For your exams are over, huh? Over. They're ongoing, huh? For you, no exam. Done. No exam. Huh? Done. Okay. What about you? They're ongoing, huh? How many more are there? When is it getting over? 19th April. So next Wednesday, till then, class can be done. It gets over on Monday. No? I didn't get you, Mayor. Can you put down your mask and talk? So leave it to Kerala. Then attend from online. Attend online. We are talking about next week's class. Attend online. You have a provision, no? Like you have good signal in the place you are going, or okay. You see, I think that should not be a problem. Shall we get started? Yep. So what did you say was the previous problem we were dealing? We were dealing with work, energy, and power, but I remember. We did problem based on graph, no, completely. That's right. So we'll get started. So did I explain the concept of conservation of mechanical energy? When conservative forces are acting on the system, the total mechanical energy of the system is constant. I would have explained two theorems. One is energy conservation and the second is. So did I explain both? So did I explain what is the meaning of conservative and non-conservative forces? I remember, I'm just asking you. So what are conservative forces? If the work done by a force in a round trip is 0, you call them as the conservative force. And most important point related to conservative forces, they are, check the last point, they are something independent. They are path independent. Right? They are path independent. And secondly, what are non-conservative forces? If the work done by a force in a round trip is not equal to 0, they are said to be non-conservative. And mostly what kind of forces are non-conservative? They are resistive forces, which are non-conservative in nature. Now, what we are going to do is, we are going to discuss another concept actually, but in your NCERT it is given as a problem. But it is actually a concept. Okay, it's called as vertical circular motion. I'll tell you what is the page number in your NCERT, page number 122. Right. So in page 122, example 6.7, there is a problem. Okay. So if at all you have textbook, you can open and see. You have? No? So those who are online, I hope you guys are having a textbook.
Yes, sir.
So if you check that, then what is the question given? Example 6.7. It says there is a string with a bob that is suspended vertically, right? Suspended by, underline the word, light string of length L. So there is a bob that is suspended by a light string of length L. It is imparted a horizontal velocity V0 at the lowermost point A, such that it completes a semicircular trajectory in the vertical plane. So it turns like this, right? When you give a velocity, what will happen to it? It starts traveling in a circular path like this. So when this is happening, it is able to complete a semicircular trajectory in the vertical plane with the string becoming slack at the topmost point C. So here the string is slack. Am I right? Obtain an expression for V0, the speeds of the object at point B and C, the ratio of the kinetic energy at point B and point C. Okay. So are you guys able to visualize this? What happens is there is a bob that is suspended. If you give a horizontal velocity, it starts rotating in a circular trajectory as shown in the diagram. Right? So when this is the scenario, now the question is, what should be the minimum velocity that you need to give at the bottom so that it is able to complete a semicircular trajectory? Right. So for that, we are going to proceed like this. So there are certain equations that we are going to form. So the hint or the idea to solve this problem is we need to apply Newton's laws of motion, right? We need to apply Newton's laws of motion and energy conservation theory. So these are the two things that we are going to apply. Is it clear? Right? Now, if I take at point A, if I take it at point A, then what is going to happen is the bob is going to get suspended in this way. Right? So at point A, if you see, the weight of the bob is in downward direction, which I'll call it as mg, and tension is acting in the upward direction. Right? And if you see, the particle is revolving in a circular motion. right? So for any object to be in a circular motion, the necessary force is the centripetal force. When that is going to be the scenario, now here the speed is V naught, then what I will do is T minus mg, or to be more specific, I will say, if I take this as A, then TA minus mg is equal to mv naught square divided by L, because L is going to be the radius of the circular orbit, right? So let this be equation number 1. So this equation is obtained using the Newton's laws of motion. Now what we will do is, if I take the bottommost point as the reference point, if I draw a line through the bottommost point and I'll call it as the reference line, means that point is taken to be the origin, right? So with respect to that, what are all the energies possessed by the object? So if I ask you, what is the total energy of the system at point A? The total energy is always contributed by two components. One is kinetic energy at point A plus potential energy at point A, right? So the total energy at A is equal to, what is going to be the kinetic energy at A? It is half m v naught square plus what is going to be the potential energy? It is going to be 0. Here. So this is going to be 2. Right? Am I clear with this? Make a note of it. Clear. Right? Shall I move on? Whenever you calculate the potential energy through the reference line, it is always zero. Similarly, if I take at point B, so B is here, right? There is a force acting like this. Mg is in this direction. Tension is in this direction. So here I'll call it as TB, and the speed I'll call it as VB. So can I say, according to the Newton's law of motion, TB is equal to m into VB square divided by L. Right? So let this be equation number 2. We'll make it as 3. So let this be equation number 3. Right? Now, the total energy at point B is equal to the kinetic energy at B plus the potential energy at B. So what is the kinetic energy at B? Kinetic energy at B is going to be equal to half into m into VB square, and the potential energy at B is going to be equal to, if I take this to be the line, the height to which the object has raised is the length of the string. So I will write it as m into G into L, and let this be equation number 4. Okay, just a minute. Clear with this? Similarly, if I take it at point C, then that is going to be the topmost point. And here, if I call the velocity to be Vc, so with respect to the reference line, the object has raised a distance of 2L, that is a diameter, right? And according to the Newton's law of motion, here what is going to happen is, if I draw a free body diagram, mg is in downward direction and tc is also in the downward direction, and speed is going to be in the leftward direction. So can I write T plus mg is equal to m into vc square divided by L, right? But here, a point to be noted is, at point C, string becomes slack. So tension is 0. So when tension is 0, you take this value and substitute it here, then you will get mg is equal to m into vc square divided by L. M and m will get cancelled, which implies vc square is equal to gl, or vc is equal to root of gl. Okay, let me call this as equation number 5. Make a note. Right? So moving on to the next equation. So if I take the total energy at point C, that will be the kinetic energy at point C plus the potential energy at point C. So what is the kinetic energy at point C? It is half into m into Vc square, and the potential energy at point C is going to be mg into the height with respect to the reference line is 2L. So this will be equal to half into m into, we know that Vc is equal to root GL, or Vc square is GL. So if I substitute Vc square as G into L plus this as mg into 2L, we get the answer as 5 by 2 times mg into L, and this is going to be the total energy at point C. Now, we know the fact that since the whole system is acting under conservative forces, total energy at point A is equal to the total energy at B is equal to the total energy at C. So what is the total energy at A? It is half m V naught square. Total energy at B is half m VB square plus mgl. And total energy at C is 5 by 2 mgl. So total energy at A is half m V naught square is equal to the total energy at B is half m VB square plus mgl, and this should be equal to the total energy at C, it is 5 by 2 times mgl. Now, if I take the first and the last term, then I get half m v naught square is equal to 5 by 2 times mg into L. M and m will get cancelled, 2 and 2 will get cancelled, which implies v naught square is equal to GL, 5 GL, and v naught will be equal to root of 5 into G into L. So this is going to be the velocity that is required for the object to complete the circular track. So this is the minimum velocity at the bottommost point. Clear? Now, if I take the second term and the last term, that is half m vb square plus mgl is equal to 5 by 2 times mgl, then we get half m vb square is equal to 5 by 2 mgl minus mg into L. That will be 3 by 2 times mg into L. So 2 and 2 will get cancelled, m is gone. So Vb square will be equal to 3 into G into L, which implies Vb will be equal to root of 3 into G into L. So from this, we can conclude that the velocity at point A is root 5GL, velocity at point B is root 3GL, and velocity at point C will be equal to root of G into L. Now, having this in mind, if you try to calculate the kinetic energy at B to the kinetic energy at point C, so kinetic energy at B is going to be equal to half into m into Vb square divided by kinetic energy at C is half into m into Vc square. So half m and half m are gone. Vb square is 3GL, Vc square is GL. Both get cancelled. Answer will be 3:1. So is it clear? So this is all about the motion called as vertical circular motion. Clear? So make a note of it. Done? Not it? point. Total energy at point C. Okay, what is the doubt there? Where did VC square become GL? I didn't get your question. You didn't understand VC square. Kinetic energy, half mv square. Next slide you want to see, or you're done? Are you done with this? Tell me. Because kinetic energy is proportional to square, how will root exist? Done. Okay. So right now the next heading as potential energy of a spring. But first, we need to understand that when you have a spring, right? So spring has the functionality of getting elongated or compressed. So basically spring is an elastic material, right? So when you talk about it, when it is either getting expanded or compressed, it is happening due to a force that is existing within itself called as the restoring force. So why do we call it as restoring? Is because when will it try to get elongated on its own? See, if I have a spring like this, I try to apply a force from both the direction and compress it, then what will happen to it? Obviously, it will get compressed, but as soon as you release, what will happen? It starts getting elongated, means it will try to come back to its original shape. In a similar way, if I have a spring and I applied a pulling force, which is elongating the spring, and you release it, what will happen after some time? It will try to get compressed and come back to its original form. So can I call that kind of a phenomenon as restoring itself? Means it's trying to come back to its original shape, right? So it will be able to come back only when there is a force acting on the object, and that force should cause some displacement, right? So here, when you release everything, right, it is understood that there is some force which is stored within the spring itself. What is happening? The force is stored within the spring itself, which is actually causing this elongation or compression after the removal of force, right? So if you see what that force is, we call it as spring force. And if you observe what a spring force is an example of variable force, right? At the same time, it is conservative, right? So this is what happens. Now, if you consider a spring to be light, or I can call it as massless, right? Then what will happen is there is a force called spring force F with a subscript S. So Fs starts occurring, which is proportional to the displacement cost, which is proportional to the displacement cost, meaning Fs, the spring force, is observed to be directly proportional to the extent to which you try to compress it or elongate it, right? Suppose, I'll explain it, listen. Suppose this is the original length of the spring, right? Let's say the spring is fixed at one of the ends. Now, this end fixed, you're doing nothing, okay? So what you're going to do is you started applying a compressing force. So what has happened to it? The windings will start coming close to each other, right? Then this is the displacement that has caused on the spring compared to its original length. Then what you can say is there will be a force that will get stored within the spring, which we call it as restoring force, which is observed to be directly proportional to the amount of displacement that we caused on the object. So Fs is directly proportional to X, which implies Fs will be equal to negative of a constant called as K into X. So the reason why we are using negative sign here is because it is acting opposite to the external force, one thing. And the constant that you have introduced is called as a spring constant, right? And the unit for spring constant is given as Newton per meter. So are you able to understand this? Right. So this is the reason why in the beginning I told that spring force is an example of variable force, because what is variable force? If the force is a function of displacement, we call it as a variable force. So here, if you see, force is a function of displacement. So make a note till here. Is it clear? Shall I proceed? Because it is acting opposite to the external force. Right? Compress the spring. When you compress it, the spring force will act in the opposite direction. When you elongate it, spring force will act in the opposite direction. So whether you compress or elongate, the spring force is always opposite to the external force. That is why that minus is there. And K has no sign. Are you able to understand? Spring forces cannot call it as resistive. If it is resistive force, it cannot be conservative in nature. Obviously, because it is that has a different application. It is opposing for a completely different reason. Right, but you cannot call it as a resistive force. It is only a resistive force to the external force that you are trying to apply. That's it. It is not obstructing the motion or something. Are you clear? Shall I proceed? Now see, if you observe, the heading is potential energy of a spring, right? So I already told you, whenever you need to calculate energy, there is no direct formula for energy. We arrive at a mathematical expression for energy only by calculating work done. So we are going to calculate the value of energy only by calculating the work done. So for that, let us take a scenario like this. Let's say there is a spring which is fixed at one of the ends and it is at its natural length. Now you start applying a pulling force, capital F, which is trying to extend the spring, to the maximum value XM. Means beyond that, you cannot extend it. Its maximum elasticity is obtained. Now the question is, what is going to be the work done by the spring force? So here if you observe, there are two forces acting. One is the external force and the second is the spring force or the restoring force that is coming into picture. Right? So what is going to be the work done by the spring force? So we understood that spring force is a variable force. So work done by the spring force, can I write it as integral of Fs into dx? Right. So this is how we calculate the work done for variable forces. But the question is, from where to where is it extending from? So when it was at natural length, the extension that occurred in the spring was 0. Whereas when it went to the maximum value, it is xm. Right? So having this in mind, we can understand that 0 to xm, this Fs can be written as minus k into xm into dx. Right? Correction. Integral of 0 to xm, and this Fs can be written as minus kx into dx. Right? So if I take minus k outside, I'll have integral of x dx between 0 to xm. So this will be minus k into x square divided by 2 between 0 to xm. So if I start substituting the values here, then we will get minus k into xm square by 2 plus 0. So this will be equal to minus k into xm square by 2 And this is the work done by the spring force, which will start appearing in the form of elastic potential energy. So the actual expression for elastic potential energy is minus K divided by 2 into xm square, right? So this is the value of potential energy that is getting stored in the spring, right? Make a note of it. Clear? So once you're done, I'll proceed, right? So based on this concept, let us understand the same as a graphical representation. Okay. Suppose I have a graph that shows the variation of force versus displacement. So what does the spring force mathematically express? We know that Fs is equal to minus K into x. So when Fs is equal to minus K into x, when you draw, it will be a straight line passing through the origin like this. So if this is going to be 0 and this is xm, which is the maximum elongation taking place in the spring, when you drop a perpendicular here, then this area is going to be minus K into xm square divided by 2. Okay. So basically, when you draw a graph between the force and the displacement for a spring force and calculate the area made by the graph between the points 0 to xm, that area's value is going to be minus K into xm square divided by 2. Okay, make a note of it. Done? So based on this concept, let us try to solve the example number 6.8. To simulate car accidents, auto manufacturers study the collision of moving cars with mounted springs of different spring constants. So consider a typical simulation with a car of mass. There is a car of mass 1000 kilogram moving with a speed of 18 kilometer per hour. So 18 kilometer per hour is going to be 5 meter per second. On a smooth road, so the road is smooth, on a smooth road and colliding with a horizontally mounted spring whose spring constant is 6.25 into 10 power 3 Newton per meter. What is the maximum compression in the spring? Right? If you see, the solution, then the car moving towards the spring has kinetic energy of how much value? Of half into m into v square. Right? So let this be equation number 1. After collision, let's say spring is compressed to a maximum value of xm. Then the energy stored in the spring is half k into xm square. Let this be 2. So here if you observe, when we derive the formula for kinetic energy, when we derived the value for potential energy of a spring, we got minus half into k into xm square. But why did I use a minus here? Because there we calculated the work done. Work done can either be positive, negative, or 0. But energy is always positive. Right? So the whole kinetic energy of the car after coming to rest gets converted to the elastic potential energy of the spring. So it's very simple. We need to equate the first and the second equation. So if that is the case, half mv square will be equal to half into k into xm square. Half and half are gone. So what is going to be the mass of this car? That is 1000 into speed is going to be 5 meter per second. That is going to be 25 is equal to k is 6.25 into 10 power 3 into xm square. 1, 2, 3 and 10 power 3 are gone. So 25 will cancel this 0.25 times. So xm square will be equal to 1 divided by 0.25, or this can be written as 1 divided by 25 by 100. This goes to the numerator. So 100 divided by 25, or this is also equal to 4. So xm square is 4 will give you xm as 2. So there will be a compression of 2 meter taking place in the spring by the time car comes to rest. Right? So make a note of this. Are you all clear with what I did? So since the road was smooth, I applied energy conservation theorem. Had the road been rough, will I be able to apply energy conservation? No. But am I allowed to apply work energy theorem? Check and tell me. So when frictional force is there, you cannot apply work energy theorem. Is that what you're saying? Think and tell. Work energy theorem itself is there only to apply when whether you have conservative or non-conservative forces. When you have only conservative forces acting on the system, then you can apply only energy conservation theorem. Whereas whether you have conservative or non-conservative forces acting, you can always apply work energy theorem. By telling this, what I mean is, in this case also you can apply work energy theorem. Okay, I'll write and show you. See. Alternate way is by solving using work energy theorem. So what does work energy theorem state? Sum of work done by all forces is equal to change in kinetic energy. So here if you observe, who is doing the work to stop the car? It is the spring. So there is only one work done, that is a work done by the spring, is what is causing the change in kinetic energy of that car. So what is the work done by the spring? It is minus half into k into xm square. Because work done can be negative, and we know that the work done by the spring force is negative, is equal to change in kinetic energy. Change in kinetic energy means final. So when the car has come to rest, what will be the final kinetic energy? 0. Minus, what is the initial kinetic energy? It is half mv square. So minus half k xm square is equal to minus half mv square. Half and half are gone, minus and minus are also gone. If you observe, you are going to get the same expression as we wrote in the previous case. So they both are the same. Only thing you need to be careful with is when you're applying energy conservation, irrespective of whatever is the formula of that energy, you should always write the positive value. Whereas when you're applying work energy theorem, you need to clarify whether the work done is positive or negative. Depending on that, you need to give the sign to the work. Or else you'll get wrong answer. Had I not put sign, what would have happened? This side I would have had minus, this side I would have had plus. And you will face a situation where two squares are equal, but you have a minus. You cannot solve. Clear? So that's the logic. So work energy theorem is universal. Whether you have only conservative forces or only non-conservative forces or combination of both, you can apply work energy theorem. So you need not think about whether conservative is there or not conservative. Whereas if you have to apply energy conservation, what is mandatory? There should only be conservative forces. So and why did they apply it in this case? Because it is smooth surface. Okay. Done? Shall I proceed? Make it fast. See, write down the values alone, calculations, you do it later. So proceeding to the next question. That is example 6.9. So in example 6.9, they're saying, consider example 6.8. Now taking the coefficient of friction mu as 0.5, calculate maximum compression in the spring. Okay. So this is going to be 1000 kilogram, right? In this case, since the road is rough in nature, right? So when the road is going to be rough in nature, what can we conclude? We cannot apply energy conservation theorem. Rather, we will apply the work energy theorem. Right. So the work energy theorem says total work done by all forces in the system is equal to change in kinetic energy. So what is the total work done by all the forces? What are all the forces acting on it in the first place? One is frictional force, right? Work done by the kinetic friction. One is work done by the friction plus work done by the spring is equal to the change in kinetic energy. So what is going to be the work done by the friction? It is mu mg into the displacement. So the displacement is xm because friction is going to act till the maximum compression is going to take place. Plus, what is the work done by the spring force? It is minus half into k into xm square is equal to what is the change in kinetic energy? It is going to be 0 minus half mv square. Now, if you observe, this mu mg into xm is also going to be negative because the angle between the frictional force and the displacement are going to be 180 degrees, right? When that is the scenario, the minus sign gets cancelled, which implies mu mg into xm plus half into k xm square is equal to half mv square, right? Now, if you take the 2 to the other side, it becomes 2 mu mg into xm plus k xm square is equal to mv square. So which implies k times xm square plus 2 mu mg into xm minus mv square is equal to 0. Right? Then we can say xm is equal to, so when you have ax square plus bx plus c is equal to 0, what is the value of x? Minus b plus or minus root of y. So x is equal to minus 2 mu mg plus or minus root of b square. That is 4 mu square m square g square minus 4 into k into mv square, the whole divided by 2a, which is going to be 2k. Now, having all these values, if you substitute it here and calculate, then you will get the value of xm as 1.35 meter. Now, here, an important point to be noted is when the surface was smooth, the value of xm came out to be 2 meter, whereas the same surface when it was rough, the value comes out to be 1.35 meter. So it is decreasing. And why is this happening? Because in the previous case, when the road was smooth, in the previous case, the work that was done on the car was only by the spring. So that is work done on the car was only by spring. Whereas when you talk about the rough surface, work done on the car is by spring and friction. So since two forces are doing work on the object could not travel to the desired distance. So that is why it could travel only to a lesser distance of 1.35 meter. Are you able to understand? So this is what happens. So make a note of it. One should be negative. Because it's a distance. Distance cannot be negative. Later. Let me know once you're done. Done? So write down the next heading as power. So we saw what is work, what is energy. Now we are going to concentrate on what is power. Okay. Power is defined as the rate of doing work. Means it defined as like this amount of work done per unit time. So when you talk about power, there are two powers that come into picture. One is called as average value and the second is called as instantaneous value. Okay. So when I talk about average value, the average power is defined as total work done per total time, or I will say work done per total time. So W divided by T is what is going to be the average power. The next value that we can define is instantaneous power. So instantaneous power is defined as, write it down, the limiting value of average power interval approach to zero. Meaning, if I write something like this, limit t tends to 0, w divided by t, then this is written as dw divided by dt. So whenever you have instantaneous value, you'll always have a differential coefficient, right? So it is dw by dt. If I have to put it in the simplest possible form, we'll say instantaneous power is the power of power at the particular instant. That's it. So whenever you want to calculate the average power, what are we supposed to do? You need to calculate the total work, total time, divide both. When you want to calculate the instantaneous power, differentiate the work done with respect to time. Right. Okay. If a force F is applied on an object to cause a displacement of dr, right? Then the small amount of work dw done on the object is dw is equal to f dot dr. Okay. Now, if I define the power as dw divided by dt, so dw is f dot dr divided by dt. So this will be equal to f dot dr divided by dt, or this will be equal to f dot d. Is it clear? So power is basically the dot product of force vector and velocity vector. So power is the dot product of the force vector and the velocity vector. Okay. Now see, since power is a dot product, it is a scalar quantity. It is a scalar quantity. Now, the unit of power is what we are going to see. If I see the SI unit of power, so how is power defined as? Power is equal to dW divided by dt. So when you take the SI unit of power, work done is measured in terms of joule divided by the time is measured obviously in terms of second. So joule per second is called as watt, which is written as capital W. It was named after a scientist named James Watt. Okay. And if you see the dimensional formula of it, so what is going to be the dimensional formula? It is going to be mL square T minus C. Right? Here, now if you see, this watt is one of the units of power. Similarly, when it comes to a different applications like automobile, right? When you talk about the power in that case, it is expressed in terms of horsepower. Okay. And another unit of power is horsepower, and 1 horsepower is defined as 746 watt. Right. So this is the power used to express the output of motorbikes and everything. Motorbikes, cars, right? Similarly, we have the electrical unit of energy. So this you would have learned in your 10th grade. Suppose there is a 40-watt bulb which is running for 8 hours. How much is the power, or how much is the energy consumed by it? Right. So like this, we have something called as 1 kilowatt hour. Right. This is called as the electrical unit of energy, or it is a commercial unit of energy. Okay. So how do you define 1 kilowatt hour in terms of joule? So 1 kilowatt hour in terms of joule is represented like 1 kilo is 1000 into watt into 1 hour comprises of how many seconds? It consists of 3600 seconds. So when you calculate this, you will get the value as 3.6 into 10 power 6 watt second, but watt second is going to be joule. So in the commercial unit of energy also, we have this 1 kilowatt hour. That watt is there. Are you able to understand? So, but here, as I mentioned, you need to understand that kilowatt hour is the unit of energy. I repeat it. It is not the unit of power. Okay. You're done. So based on this, we will do an example problem. So let's do example 6.11, the 11th example. So an elevator can carry a maximum load of 1800 kilogram, which is basically elevator plus passengers, right? It is moving upwards with a constant speed of 2 meters per second. The frictional force opposing the motion. So small f opposing the motion is given as 4000 Newton. Determine the minimum power delivered by the motor to the elevator in watts as well as in terms of horsepower. So you have an elevator and there is a rope that is pulling it up. So elevator plus passenger, what is the maximum mass that it can take? It is 1800 kilogram, and the frictional force that is opposing the motion. So when the elevator is moving up, the frictional force is acting in the downward direction. So it is weight that is acting in the downward direction plus frictional force. So if you calculate the total force on the elevator, it is the weight of the object mg plus f. So what is the value of m? It is 1800 and g we will approximate it to 10 plus what is the frictional force? It is going to be 4000. So how much is going to be the answer? 18,000 plus 4,000 is 22,000 Newton. Now, what is going to be the power? Power will be equal to F vector dot V vector. Right. So F into V into, I will write it as cos 0 because whatever direction the force is applied, that is the direction in which velocity is attained by the object. So what is going to be the force? That is 22,000 into what is going to be the speed with which it is moving? It is going to be 2, and the answer is going to be 44,000 watt or 4.4 into, sorry, or 44 into 10 power 3 watt. Right. So if you want to write the same thing in terms of horsepower, we know that 1 horsepower is equal to 746 watt. Then here it will be 44 into 10 power 3 watt, which is in terms of how many horsepower. So it is 44 into 10 power 3 divided by 746. Calculate the value. That will be the answer. So the answer comes out to be 59 horsepower. So this is all about power. Okay. So one last concept that is left out in this chapter is collisions. So about which we will complete it tomorrow. So collisions is the last part, right? So I hope it is clear to this. So make a note. So there should be a slightly greater force. So when the force in the upward direction is slightly greater than 22,000, it starts moving. But slightly greater, we can't take the exact number. So we take. Here. So about collisions, we'll discuss tomorrow and we'll do some problems based on.
Thank you, sir.
Done? So ending this session. Can I?